is happening? Okay, probably something wrong with this tab. Okay, it is not. It will be difficult for me to fix it now, but please bear it. Okay, if we have, for example, a product of signal in the time domain, say GT and XT, the corresponding operation in the frequency domain will be this. That means 1 by 2 pi convolution of Fourier transform of GT and XT. If any one of these signal GT or XT is periodic, then the corresponding Fourier transform will be a series of impulses. In this case, your signal XT is considered as periodic, so this is what its Fourier transform. Now you know that xk is a scaling factor, and these are the impulses shifted in omega axis at integer multiple of fundamental frequencies k omega 0. So when we will be convolving a function of omega with these impulses, what will happen? This function will be shifted to the location of the impulses. So as a result, the frequency omega of g omega will be shifted by an amount determined by k omega 0. So the resulting output y0 omega would be, because a 2 pi was there with this factor that is cancelled. So this is what your transform of your output, that it will be a shifted version of the spectrum of g omega, and it is scaled by a factor that is what the Fourier coefficient of your signal xj xt. Okay, this has applications in sampling. Okay, consider this is the example where because today I plan to cover many things, but tab is not working properly, then how should I continue? Okay, practically what it happens, for example, say we have a signal. That signal is band limited type xt. This signal, okay, you can also think in the reverse way, because we assume the signal xt as periodic. So this is what the Fourier transform of this periodic signal. It contains series of impulses from minus k to from minus k to plus k, because in both negative and omega, negative and positive frequencies, the Fourier coefficients exist, and they are appearing. They are appearing as conjugate pairs. If they are appearing in conjugate pairs, then this side is for k minus k, this side is for plus k. So this is what the impulse is appearing at the location of harmonic frequencies. Now, and this is what is GT, a band limited signal with a bandwidth is equal to W. Then if this negative side is actually because of the mathematics. Now, if we convolve them together, what will happen? We know that if we convolve an impulse with a signal, the signal is shifted to the location of the impulses. Here your signal is in the frequency domain. So if this is what the spectrum of your signal, then what will happen if we convolve it with this impulse? This is what that signal, it will not be going elsewhere. Then if we convolve our signal, this signal with this impulse, that impulse is located at delta omega minus omega 0. Very difficult. I don't know what happened. So your delta omega, I cannot write actually. How to proceed? it is delta omega minus omega 0. If we convolve a signal with g omega with this delta, jg omega will be shifted to the location of the delta. This is what that shifted version of the spectrum. The scaling factor is there for this region that the amplitude is reduced. In the same way, if we consider this delta, the negative is there, so it is flipped. And this is what the shifted version, this is shifted further to twice omega. In this way, the spectrum of your resulting signal will be shifted in this way. So the conclusion is what? If we multiply two signals, a periodic one and a non-periodic one, then the spectrum of the non-periodic signal will be appearing as a shifted version in the product. Okay, this is an example of a multiplication of a square wave with a signal. That signal is, for example, shown in figure 4.4a. What is that? If you have your book, please open up your book and look it out. Okay, in 4.4a, it is actually a square wave.
Yes, sir.
Periodic square wave, isn't it? So if it is a square wave, then we can easily Fourier analyze it into Fourier series. Then this will be the Fourier coefficient xk. Then our objective is what? We need to find yj omega. That is a multiplication of a signal gt with xt. Your gt is given as what? Your gt is cos t divided by 2. So you know that for cos t divided by 2, what is the Fourier transform? You will have two values of your spectrum appearing at one frequency here, another frequency there, okay? The first one is what? Because your frequency here is equal to what? In this signal, omega equal to what? Omega is equal to half, isn't it? So if it is half, yes, then sir. One is appearing at minus half, another is appearing at half. Isn't it? Yes, so your omega 0 is not only half, actually, in this case, your omega is appearing as well, because you see the periodic signal is there. So our g omega is this, and we have our periodic signal, for example, already we have with us. Then what will happen? The g will be shifted at the location of the harmonic frequency scale, isn't it? So then you can easily identify that this would be the corresponding yj omega, because your gj omega is this, the Fourier transform. EPP shifted to where? At the location of harmonic frequencies. Then a minus term and plus term, minus term will be there. That is what? The shifted location of your harmonic frequencies k pi by 2. Because in our case, omega 0, omega 0 is equal to, for you signal, periodic signal, it was given in 4.4a, and omega 0 was equal to pi divided by 2. Very difficult because I cannot write with this pen. I don't know why this is happening. I need to calibrate it. Wait, can you hold for a few minutes, please? I just let me
Okay, sir.
calibrate it because it is difficult. Just no I am Okay, are you there?
Yes, sir.
Okay, now it is fixed. Okay, so this is our spectrum, and probably we are talking about an example. Okay, this is actually a square wave. You know that the square wave is a periodic signal, and that periodic signal can be Fourier analyzed to find the Fourier constant xk. That xk will contain this harmonic amplitude. Then what we can do by using our foregoing equation, we can easily find that this is what your xk, this is the shifted version of the spectrum of the another signal that is not periodic. In our case, it was cosine omega t, something like this, and this signal has this amplitude. This Fourier transform. You know that Fourier transform of cosine omega t is a finite frequency signal will have two values. One is at minus half, another will be at half with amplitude equal to pi. So this is what this thing. Then if we just put this thing into this equation, your corresponding frequency component will be shifted by k pi by 2. So this is what the locations of our spectrum after multiplication of a signal. Okay, we will. One of the important application of this property is in your modulation. You see, in the communication engineering, when we obtained a band limited signal, baseband communication may not be possible because of energy and other issues. For this reason, what you need to do, we have to modulate the signal with high frequency signals so that your spectrum will be shifted to higher frequency locations. Then this can be transmitted from one place to another, either by using wired media or it can be in wireless transmission. One of such modulation technique is amplitude modulation. It is widely used, probably the most earliest type of modulation we use. Still, it is being used. So what you usually do in this case, you see how multiplication operation is coming into being. Okay, you see that if we have a signal MT, this is your message signal. Then your message signal is actually a finite bandwidth signal. Consider that this is your message signal. If we Fourier analyze it, this can be the spectrum of your message signal. It is certainly a band limited signal. So if it is a band limited signal, a finite bandwidth is there. And that frequency, for example, is a bit at a low frequency. Energy of your message signal is also very low. Now, if we apply this signal to a multiplier and we are multiplying it with a cosine omega t, say this is sometimes called carrier signal. Probably you know the term carrier, okay? Have you heard about carrier term in your communication engineering?
Yes, sir.
So
Yes, sir.
this is a carrier signal. If we multiply the signal with a carrier with higher frequency, then what it happens, according to our foregoing analysis, multiplication in time domain, what we call a convolution in the frequency domain, isn't it? So you see that either in this case, you can convert your cos omega ct into frequency domain. Then if we convert our omega ct into frequency domain, you will see that we will have two frequencies there. One is at omega c, what we call an impulse will be there. This is your delta omega minus omega c with an amplitude equal to pi. Similarly, another impulse will be there at minus omega c with amplitude. This is your pi delta omega plus omega c, isn't it? Now,
Yes, sir.
if we convolve, now this is your what? This is your carrier spectrum. And this is your what spectrum? Message spectrum, isn't it? If these two things are there, then how can we find the resulting spectrum after multiplication? The resulting spectrum of your signal, say this is your RT, then Rj omega would be equal to what? You have two ways to do that. Either you can I use this property of Fourier transformation, that when a signal is multiplied by e to the power j omega t, it will be shifted in frequency. Frequency shift property can be applied there, or you can use the convolution property that both will give you the same result. Rj omega would be equal to 1 divided by twice pi, message signal aj omega, convolution, say carrier signal c j omega. In our case, it will be equal to 1 divided by twice pi m j omega, convolution with pi delta omega plus omega c plus pi delta omega minus omega c, isn't it?
Yes, sir.
Yes, sir.
Yes, sir.
So what will happen then? If we convolve your mj omega with this delta, your mj omega will be shifted to the location of minus omega c. And
Yes, sir.
Yes,
when
sir.
we convolve our mj omega with omega minus omega c, it will be shifted to the location of omega c.
Omega C. Yes, sir.
So in this way, you can easily find that spectrum, the message spectrum, is shifted to the high frequency band centered at omega c. For this reason, sometimes this frequency omega c, the carrier frequency, of course, we frequency can be scaled either in radian per second or in hertz. So in our case, as we are referring omega, that our case will be radian per second, the angular frequency. Then you see that your spectrum of your message signal is shifted in either direction in this way, isn't it? The half amplitude is coming because of convolution scaling. So this is what the spectrum of your modulated signal. You see that your spectrum is centered at omega c, okay? And you will have a frequency there, you will have a frequency there. That frequency equal to what? If we consider that frequency was W, this is equal to omega c minus W. This is equal to omega c plus W, isn't it?
Yes, sir.
So with this thing, if we write this thing, okay, what is the, in general, what is the name of this type of, we call it amplitude modulation, but in terms of frequency, it is also called what? Double sideband type, isn't it?
Double sideband.
Okay, we have two sidebands appearing, isn't it? One is called lower sideband, another is called upper sideband. This is your LSB, lower sideband, okay, LSB. And this is your upper sideband, okay? Okay, in both sideband, we can consider only your half of your spectrum there to communicate. Actually, this carrier will not convey any information. It will be using as a vehicle, okay, to transmit your signal from one place to another. In this way, you can easily identify how this can be done. Now, once your signal is transferred into a high frequency band and you are transmitting, at the receiving end, what will happen? You have to bring back your signal, isn't it?
Yes, sir.
How that that we call demodulation, isn't it? How
Yes,
demodulation is performed?
Multiplying the
Yes, that means you have to generate. That is called heterodyning. Okay, what you need to do, you have to use another carrier with same frequency. You have to generate at the receiver, and again you multiply your receive signal with that carrier. Then what will happen? Then your frequency will again be coming back to your okay. Then a spectrum will be equal to what will be the resulting spectrum. Consider that we have just, I am giving this explanation by simple intuition. The rest of the thing you explore it with the experience of your communication engineering. You see, now at the receiving end, what will happen? Receiving, say your transmission is happening in ideal case, no loss, no distortions are there. Then our signal RT is available at the receiver. Again, at the receiver, we are creating another carrier with same frequency, isn't it? We are multiplying it in this way. You got the point?
Yes, sir.
Yes, sir.
And that multiplication will, what will happen then? This multiplication in the frequency domain will be equal to 1 by twice pi Rj omega convolution. This quantity pi delta omega plus omega c plus pi delta omega minus omega c, isn't it?
Yes, sir.
Yes, sir.
The once we again, then what will happen? The spectrum will be shifted at the location of omega c, is it?
Also minus omega c.
So omega
Yes.
C plus omega C and another is omega C minus.
Omega. That means this figure is shifted at where?
And 0 and 2
Zero and
omega c.
At this point, the 0 will be shifted here, isn't it? That means the whole figure, for example, will be shifted in either direction. Okay, try to figure out that how your figure will look like. You will see that another spectrum will be appearing here as a result of the shift. Then what can you do? Then you apply a low pass filter there to extract this portion out. Can you draw the figure? If we shift the whole figure to minus omega c and plus omega c, you see that when we shift this figure to minus omega c, this position will be coming at 0, isn't it?
Yes, sir.
Yes, sir.
Then I am not talking about all other frequencies. I am just interested in what is present there at with a frequency, that is what is present there. For example, centered to omega equal to 0, because this resembles exactly to your original signal, isn't it?
Yes, sir.
Yes, sir.
So what happened then? With this multiplication with the carrier, again you are bringing back, you shifted a spectrum of your message signal at the original location, but an amplitude factor will be there. Then you can tune the gain of your low pass filter to mitigate this amplitude. Then what will happen then? You just apply this after receiving your modulated signal, again you multiply it with your carrier generated at the receiver, local carrier, by using a local oscillator.
Sir, I have a question here.
Yes, please.
Sir, if we pass the signal through a low pass filter, shouldn't it be the negative 2 omega C signal also?
Okay, you see that these are the mathematics. Okay, it is not happening in your device. In your device, only this portion 0 to omega. This portion is enough to reconstruct your signal in real time. You do not need minus omega. Minus omega is coming here because of mathematics. But when we are using it in our real thing, only this push, because a real low pass filter will have this spectrum, okay? Say this type of frequency spectrum. Then only this portion of your signal is there just to create your signal at the receiving end, okay? But minus omega is appearing here because of mathematical analysis. For example, say, can we generate e to the power so easily e to the power omega t? Rather, we are generating cosine omega ct, isn't it? The cosine omega ct can be easily generated, and your message signal is a real. So if we pass the message signal through a filter, then what will happen? Will it need any negative frequencies? No. But what we need in mathematics to understand it, we have to use, in order to generate the real signal mathematically, you need your negative frequencies, because Fourier analysis involves complex exponential, isn't it?
Yes, sir.
So in practice, negative frequency will not be involved in reality, okay? But in order to extract the thing by using mathematics, you need a negative frequency, otherwise you need. Okay, this is what the process. Already I have discussed. You got it? That when RT is received, again local oscillator is there, multiplied, that you get your ZT, for example, receive signal. Then you pass the signal through an ideal low pass filter, then you will get your YT out. So this is one of the important applications of your Fourier mathematics in analyzing your communication system. Other huge applications are there, but we do not have that much time left to investigate all other issues. But some applications there in your control engineering, some applications there in communication engineering, you have already learned it to know the frequency behavior of your system that is there, okay? So this is how your signal is extracted by a low pass filter. It is mathematically, okay? Because Hg omega is a complex quantity and frequency ranges from -infinity to infinity. Otherwise, real signal cannot be generated. But in practice, only positive frequencies are involved. Now, another important application of the multiplication properties, and from this point ahead, you will learn some interesting things, and I hope you have some introduction about it in your earlier courses. The thing is that, when we have our signal present in continuous time, sometimes your signal may appear discretely, inherently discrete, but in most of the cases, your signal will be continuous in time. But if you want to process it digitally, you have to make it discrete. After discretization of your signal, you have to truncate your signal or quantize your signal to finite levels. Then you have to code it by using some sort of coding technique. You know this thing, isn't it? PCM is one of the widely used coding technique, isn't it? Have you learned about PCM? Pulse
Yes,
code
sir.
modulation?
Yes, sir. Yes, sir.
Okay. So then after having quantization is done, what you need to do, your level will be finite. Then you can code your level with finite numbers of bits, okay? So in this way, we usually convert our signal in a continuous signal into a digital form. Digital signals are discrete, but not all discrete signals are digital. Now, in order to make this discrete signal, what you need to do, you have to sample it, isn't it? You have to put a sampler there so that after a finite numbers of intervals, your signal should be sampled, okay? One of such important sampling technique is called impulse sampling. Impulse means if we have a pulse train generated with very, very small amplitude, duration, and that can be considered a series of impulses. Theoretically, it will look like a impulse train, something like this. Then if we multiply these two signals together, then what will happen? Your signal will be there at the output, located at the location of the impulses, isn't it?
Yes, sir.
As a result, it is very similar to your sampling. By putting a switch there, for example, say you can apply, for example, your signal is there, say, this is ST signal. We are having a switch making it on and off. Then what will happen? When you see a switch is on, you will get output. When your switch is off, we will get our output. Okay, this type of sampling is used in practice. We have a zero order Holt, we have a first order Holt type circuit there. And I know that, and I must assume that as you have already attended a few courses related to digital technology or something like that, digital electronics or something like this, where you have been introduced to sample and hold. Sample and holding, why holding is needed?
So to give the quantizer and encoder enough time to.
Yeah, very good answer. Okay, very good. That means when, because you see that your signal will be going there serially, isn't it? So when a sample is entering, for example, the further processing, for example, by quantization or coding, it will take time, okay? Within that time, your signal amplitude may be thought as constant, or we call it flat top type sampling. As a result, you have to hold it. Otherwise, what will happen? If your signal will disappear, then processing will not be possible, isn't it? So that holding is needed. That holding can be made by zero order hold. That means flat top type. That means the signal is acquired fast, sensed fast, and kept the amplitude constant. But in other cases, it can change linearly, okay? That is called first order hold. There's so many things are there. Now, let us, okay, now the thing is that in what will be the rate of operating this switch? That is all sampling rate. You have to understand it mathematically. You learned it that we need at least some numbers of samples minimum to reconstruct our signal, isn't it? So in your earlier days, what criteria you have learned about in terms of sampling?
Nyquist criteria.
Nyquist criteria, okay? That means you have to sample your signal in such a way that your sampling frequency should be such that in terms of bandwidth, it rate should be greater than equal to twice of the bandwidth, isn't it?
Yes, sir.
Sampling frequency should be twice of the bandwidth of your signal. So before sampling, then what you need to know? You need to know what is the frequency content of your signal. Then you can apply sampling. Otherwise, many effects are there. These effects sometimes we call aliasing. Those things cannot be understood so easily in the time domain. But frequency domain analysis will be very easy to, for example, investigate the consequences of this sampling, okay? That we will be investigating here, and I will consider the thing in the frequency domain, not in the time domain. Now, if we have a signal, that signal is multiplied by the impulse train, then what will happen? Your output signal will be something like this, okay? That means it must be running sum. Otherwise, because the signal samples will not be appearing at a particular time, it will be appearing at integer multiple of TS for negative integers, also for positive integers, because your impulses are there both in the negative and positive time region. So this is how the sample version of your signal in time domain. Now, what you need to do, this is the amplitude of your signal at the location of impulses. This is an impulse train. We can easily Fourier transform these two, because we have now one signal xt, another signal is pt. Okay, after obtaining, for example, this signal sample version, you can Fourier transform it. It is also a periodic signal, and you can easily Fourier transform it to know the spectrum. Or what you can do, you can use your multiplication properties there to express your signal into frequency domain. In that case, what you need to do, you have to Fourier transform xt and Fourier transform pt. Pt is a periodic signal of impulses. You can easily Fourier transform it. And xt will be a band limiter signal. And that band limiter signal will have a spectrum with a certain bandwidth, okay? Then after multiplication, what will happen? This spectrum will be shifted to the location of the impulses. Let me show it. Okay, so this is what your signal after multiplication. This is a spectrum of your signal, and this is the spectrum of your series of impulses. So after having this thing done, we know that this is what the Fourier transform of a series of impulses. And this is the Fourier transform of your signal. And this factor 1 by twice pi, we are convolving them. As a result of convolution, like your previous examples, what will happen? Your spectrum xj omega will be shifted to the location of these deltas. So one will be there for k equal to 0 at the origin of omega 0. And other will be shifted at the location of omega s, isn't it? Your omega s is the sampling frequency, can be determined by twice pi divided by ts equal to omega s. You understand the thing?
Yes, sir.
That's what,
Yes, sir.
what is happening then? Your spectrum of your original signal is shifted at the location of the sampling frequencies in either direction, okay? Again, you see that negatives are mathematically. Now you see that if this is the case, then this spectrum and this spectrum are separated in frequency, isn't it? They have no any overlap region. Is there any overlap region?
No, sir.
No. Then after processing it, you can easily extract your signal back from this discrete version to continuous version, no problem, by filtering. Now the thing is that, say, what is this point actually? This point is
Omega s minus w.
omega s minus w. Very good. Omega s minus w. Can you tell me what is the limiting case of omega can be there when no overlap? When your omega w is equal to omega w is equal to omega s minus w, then this edge will be coming here, isn't it?
Yes, sir.
For example, when these two spectrum will be touching each other at this point, then at what will be the omega s then?
2W.
Omega s is equal to 2W. Very good. Now, if we, for example, decrease the frequency less than this, what will happen?
There will be interfering.
There will be an overlap between these two spectrum, isn't it? We are examining only two, but this will happen in other cases also, isn't it? That means this is very simply understood that if omega s is such that it is less than what? Twice W, then what will be happening? Twice W means twice of the bandwidth of your signal. Then what will happen in two spectrum will be overlapped, isn't it?
Yes, sir.
So this is what your limiting case. But this is not the case when omega s is less than omega 0. So what is happening then? If we want to investigate this region, you see that in this region, a frequency, higher frequency component and a lower frequency components are coexisting, isn't it?
Yes, sir.
And its signal cannot be recovered. For example, you see that the resulting spectrum becomes something like this, not like this, okay? With this spectrum, if we apply it with a low pass filter with bandwidth equal to W, then you see that this portion of your signal will be there extracted, and that is not exactly equal to this spectrum will not be exactly equal to your input signal. So your signal cannot be extracted, okay? In addition to the original signal, another high frequency signal will be coming or impersonating your original signal, okay? That particular signal is called alias of your original signal. For this reason, what you need to do, if you want to avoid this thing, you have to pre-process your signal before sampling. That is, you have to use an anti-aliasing filter there to eliminate the possible aliasing. But if we can maintain our operating the reason is that why we need this actually. Theoretically, someone can say we do not need any filtering, just we can increase our sampling rate to avoid that possible aliasing. But this is not feasible actually. The reason is that if you increase the number sampling frequency indefinitely, what will happen? That is, you are oversampling, then what will happen? It will overburden your system, isn't it? Because if more numbers of samples are there that is not required, then what will happen? The bandwidth requirement for your processing will be higher, and you will have many signals in terms of redundancy redundant. So this is not the way. You have to set an optimum frequency so that your system will be operating without overburdening its component. Now the thing is that you see that a spectrum is there occurring something like this. And a spectrum is there and another spectrum is there. Another spectrum is there, something like this. So this frequency is say W and this frequency is what? Omega S minus W, isn't it?
Sir.
So if we put a line there, you will see that this portion and that portion, can you find the shape? Is it not that this portion is folded over in this portion?
Yes, sir.
And that is what your folding frequency, okay? That means at that frequency, it will have, see that it will be folded over here. And one of this portion is actually unwanted. And that is what the aliasing. Further analysis is there. You can investigate it very simply. So in order to avoid what? The sampling, this type of situation, you have to have your sampling rate for a band limiter signal that must be greater than what? And equal to twice of the bandwidth of your signal. An example is there for sinusoidal sampling, okay? So if we sample your signal Okay, if we have say cos pi t, then how many spectrums are there?
Two.
2 at pi and minus pi, at pi and where? Okay, these things are there. Okay, we have 2 frequencies, isn't it? What is the frequency? Omega, in
Plus
terms
minus
of
pi.
omega, is equal to pi. Then in our case, what must be the sampling frequency? At least equal to twice pi, isn't it?
Yes.
In terms of omega. Now, if we maintain this thing, okay, after sampling, you see, our signal will be shifted at the location of the sampling point. So then 3 cases are studied there, you try to verify it. Now you see that if your sampling frequency is, say, in that region, 8 pi. 8 pi means our frequency was equal to twice pi, and now your sampling frequency omega is equal to 8 pi. That means 8 times of your original frequency, isn't it? Is it not your sampling? Because you see that your spectrums, these are the original spectrum of your signal, and it is shifted in either direction. Is it not this quantity omega s? Is it?
Yes, sir.
If it is omega s, you see that your omega s is equal to 8 pi. That means it is 8 times of your signal frequency, isn't it?
Yes, sir.
And they are well separated. Now, if we decrease, for example, our omega s, say 4 pi, then what will happen? Your signal will be coming here, isn't it?
Yes, sir.
And if we further decrease it, then what will happen? If we have these 2 spectrum, the discussions are there in your book as well as in this slide. Try to just have a look. Say this is your original spectrum. Now we are having, for example, our signal that is rate is less than twice pi. Then it might happen that your signal samples for the next shifted version will be coming here, isn't it? Then what will happen? These two red are for k equal to 0, and your yellow are for k equal to 1, isn't it? K equal to plus minus 1. So you see that for k equal to 1, not plus minus 1. K equal to 1. That means this is what for k equal to 1. Your k equal to 1 samples are, you see that coming within the bandwidth of your original signal. So this is actually appearing as what? Alias component in your if your sampling rate is not quite high, okay, or not satisfy the Nyquist sampling rate. Okay, this is in the frequency domain. In your time domain, this can also be studied, but it needs, for example, more mathematics to proceed with. You see that in practice, this is impulse cannot be generated in this way. Practically, what will happen? Your impulses will be approximated by thin pulses. If we have our thin pulses, then what will happen? Your signal will also be appearing as a series of thin pulses. Then if they are Fourier transformed, then you know that your pulse signal will generate a sinc function like frequency spectrum. So as a result, what will happen? If they are added together, they will generate your output. That is what is impulse response of your system. Okay, the thing is discussed here. In the time domain, your consequences will be there. This is presented in this figure. Please, explanations are there in book. If we take this figure, for example, this is what the optimum case. The sample we are taking, for example, in this way. 1 sample per 3 samples or 2 samples per period. But if we further decrease the sampling rate, you see that your sampling can be something like this. a sampling is appearing here, the blank dots, then you can easily see that this dotted curve and this solid curve was our original signal, but using the samples, for example, your open circles, okay, or blank circles, you can also draw a sinusoidal signal, something like this. And this low frequency signal becomes the alias of your original signal. Because the sampling, you cannot differentiate that whether the sample is from your original signal or the dotted signal. And this thing will be further investigated in your digital signal processing course in your next semester, inshallah. So that is what from the application side, I will be discussing few examples. Okay, you can solve some problem, but as you know that your problem will not be exactly repeated in your exam, but you can have some flavor how this problem can be solved from your book, okay? For example, say problem 4.4. In problem 4.4, very interesting problem. Do you, okay, let me share the whiteboard, because we spent few minutes uselessly. For this reason, I am short of time, because I was planning to move a bit further, but I could not do that. So you see that if we have, you see, we have learned some properties of Fourier transform, both in frequency domain and time domain. Those properties will help us, for example, to analyze our system very easily. That you need to remember, actually. The thing is that in problem 4.4, it is said that an LTI system has an impulse response HT. Impulse response HT equal to 2 cosine 40 into sine pi t divided by pi t. Okay, you have been asked to calculate the output if your input is 1 plus cos pi t plus sine 4 pi t. Okay, can you tell me in how we can proceed?
So we can convert in frequency domain.
Frequency domain, yes, because our output in the frequency domain AXJ omega, YJ omega would be equal to what? Our output in the frequency domain would be equal to multiplication of our transfer function with the input, isn't it?
Yes, sir.
So our transfer function HJ omega is nothing but Fourier transform of HT, isn't it? The first thing is what? We have to take the Fourier transform HT. This is what your HT. Now you see that if we have this function, for example, sine pi t divided by pi t, a sinc function like function, what is the Fourier transform of this function? Is it not a square, for example, of something like this, minus pi to pi with amplitude is equal to 1, is it?
Yes, sir.
Okay, that you have to remember, okay? So this thing will be equal to this. Okay. Now, when we multiply this function with what? We are multiplying it with a what function? Cosine 40. What is the consequences of this multiplication?
It will be cosine 40 from minus pi to pi.
Sorry?
It will be cosine 40 from minus pi to pi.
This multiplication, you can think in the two different ways, okay? you can consider you can express either you can use your convolution property, or you can use even in your time domain or frequency domain properties can be explored here without going to convolution. For example, AST can again be expressed as your cosine 40 equal to what? Cosine 40 equal to e to the power j40 plus e to the power minus j40 divided by 2, isn't it? So you can easily find this thing in this way, pi t by pi t. Is it okay?
Yes, sir.
So that is equal to what? E to the power j40 into sine pi t by pi t plus e to the power minus j40 into sine phi t by pi t. What is the effect of this multiplication? If frequency will be shifted to the frequency spectrum will be shifted to this location of 4 radian per second, isn't it? And frequency of this shifted will be shifted to 4 pi by location. As a result, what will be happening? This spectrum in the frequency domain, this is what your original spectrum from minus pi to pi. Now it is shifted where?
Sir, plus
In the positive side, it will be shifted to what? 4 pi. Say this is your 4 pi, say. If it is 4 pi, then this is coming here and this is coming there. This is your plus 3 pi and this is your 5 pi, isn't it? Similarly, this signal is shifted here minus 4 pi, minus, it was pi, 4 pi. Actually, it was cos 4 pi t, not 4 pi, 40, okay? You please correct it. This is 4 pi t, okay? This is 4 pi. So it will be 4 pi, then your signal will be from minus 3 pi to minus 5 pi. Now you see that this is not your spectrum now. After multiplication, this is what your Hg omega. If this is your Hg omega, then your input is your what? Input equal to xt equal to what? Your xt was equal to 1 plus cos pi t plus sine 4 pi t. Now tell me, if we apply this x to that filter, to that system, that frequency response is there, okay, like a band pass filter. Then which of these two components will be appearing at the output? You have a DC. Is your DC component appearing at the output?
no, sir.
Is cos pi t appearing at the output? Consider this color, okay? This is what your spectrum. This is no longer is there. This is your spectrum. Then is there any value of Hg omega in that frequency omega equal to pi?
No, sir.
Then can you expect any output? Can this frequency pass through this filter?
No, sir.
So the output will be 0 for this signal. That output will be 0 for this signal. Then you see that is within the bandwidth of your filter. Then your output will be this, okay? This will be, you are getting your output sine 4 pi t. So this is very simple. You need not to solve your problem rigorously. Simple intuition can give you some solutions, but practice is needed. So some other examples are there. Try to solve this thing, okay? Very similar to this thing, okay? We have a class test left, and it is scheduled on which date?
28th.
Okay, the thing is that in the 28th we have left with Laplace transform also, but I don't know to what extent we could cover. But I will consider this week's lecture and one lecture from Fourier properties that we studied earlier for the content of these classes. And your class test can be there like your last class test, okay? You will have simple questions
Yes,
there.
sir.
And did you get your mark? Not yet probably for the last class test?
No, sir.
No.
No, sir.
Most of you have done good, okay? But the thing is that the questions are very simple, but be careful about your final exam, okay? Do you think that I should take the class test in a way that I take the last class test? Yes. But it will be challenging for me to take or prepare particularly for numerical type. Numerical type will be there. In this case, your choice can be more than 5, more than 4. Okay, let us, in the weekend, I will prepare.
Sir.
What you need to do then, okay, you simply Fourier transform it, okay? If you Fourier transform it, then simply you will understand that how we can proceed with analyzing the signal, okay? Both your discrete time and continuous time signal can be analyzed in the same way. Okay, and you see that your problem 4.5. 4.5 is an example for your discrete signal. Okay, in this case, okay, just I am giving some hint. You can proceed by your own. For example, if Hn is given in this way, Hn is equal to say half Un. Okay, in solving your multiple choice questions, some are saying that some calculations and recalculation must be needed, okay? But what I am repeatedly advising you, that whenever you are encountering some representative signal, then you have to memorize, okay, how the Fourier transform will look like. For example, if we have a signal, we know that this is the impulse response in the discrete time system. You have to find the Fourier transform e to the power j omega in order to understand the filter behavior. What is the Hj omega? Because we have learned Hn is equal to alpha to the power n Un earlier, isn't it? And whose Hj omega was equal to what? Simply 1 divided by 1 minus alpha e to the power minus j omega, wasn't it?
Yes, sir.
If we can remember this thing, then what is the value of your H omega? It will be equal to 1 divided by 1 minus half e to the power minus j omega, isn't it?
Yes, sir.
And that is a periodic function, and that period will last from, we need from minus pi to pi, isn't it? Now, if we have a signal, for example, and you know the plot, don't you know the plot? Its plot was something like this, isn't it?
Yes, sir.
Only we know from minus pi to pi. Okay, if we give an input to the signal, that if we give an input to that filter system with an input of xn is equal to say 3 plus say cosine pi n plus pi by 3. We can easily Fourier analyze what are the frequencies present there. What are the frequencies present there?
So pi plus
Okay.
pi minus pi.
Then if these frequencies are present there, can you identify that which of the component we will be getting at the output? You see that region from minus pi to pi also contained a DC part at omega equal to 0, isn't it? So a DC part will be there appearing in your output. Similarly, this signal is also appearing in the output. The reason is that it is within the frequency band of your h e to the power j omega, isn't it? But some scaling factor, gain factor will be there that you have to find it out, okay? Try to solve this problem in this way. I hope you'll understand it. Very simple, okay? You need not to solve rigorously. Some intuition or intuitive approach is good enough to understand the signal, okay? So you try to get accustomed with the system For example, solve problem 4.18, 4.19 is a good problem, 4.20. Okay, you can, for example, make a computer program to solve 4.19. Okay, this is for your self-exploration. You need not to show it to me. Then you explore yourself and try to understand. 4.21, 4.20. These are the ideal problems you can handle with. Similarly, 4.22, lots of problems are there of same type. So that's it from my part today. Inshallah, next day we will be starting our Fourier Laplace transform. But I would request you, just we will not be spending time in mathematics. We will be directly going to application side with some special issues probably that has not been dealt with in a detailed way in your earlier courses. That particular point will emphasize. Okay, please respond to your calls. We have only 44 out of how many? So if I get more than this in the response, then your percentage, whole percentage will be 0. Roll number 12 for 24.
Sir, we are section B, sir.
Oh, yours. Today is Tuesday, isn't it? Okay.
Sir.
Yes, your section. 35.
Yes, sir.
9.
Yes, sir.
13.
Yes, sir.
33.
Yes, sir.
34,
Yes, sir.
48. 51. 51.
Yes, sir.
53. 54. 55. Am I connected?
Yes, sir.
Yes, sir.
55. 56. 57. Hey, all are absent?
Yes, sir.
61. 62.
Yes, sir.
64.
Yes, sir.
67.
Yes,
69. 70. 72.
Present, sir.
73.
Yes, sir.
74. 77. 78.
Yes, sir.
79. 79.
Yes, sir. Yes, sir.
80.
Yes, sir.
82.
Yes, sir.
Sir, 87.
একটু দাঁড়াও বাবা, একটু দাঁড়াও। 86.
Yes, sir.
87.
86.
Yes,
Yes,
sir.
sir.
Sir, 87.
Yes. 88. 89.
Present, sir.
91. 92.
Yes, sir.
93.
Yes, sir.
98.
Yes, sir.
99.